Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving deep into something pretty exciting. Essential Web v1.0, a massive data set of 24 trillion tokens of, get this, organized web data. What do you all think about this?
24 trillion. That's a lot. My initial reaction is, wow, that's a whole new scale we're talking about. More data has always been a path to bigger and better AI. I think this is a huge leap and brings us closer to AGI.
I'm a bit more hesitant. While the scale is impressive, the word organized is doing a lot of heavy lifting here. What does organized mean? Is it just indexed? Are there actual symbolic representations of knowledge? Or is it just a massive, well-labeled pile of text?
That's exactly what I was thinking. Organized is key. Does it reveal some kind of inherent structure? Maybe a latent coordinate system within the web itself. That would be far more exciting than just more text for a language model to chew on.
Well, look at the history of deep learning. Every time we've scaled up the data and the model size, we've seen significant improvements in performance. GPT-3 was a massive jump over its predecessors, and it was primarily driven by scale. 24 trillion tokens gives us a chance to learn even more subtle patterns and relationships in the data. We're talking about models grasping nuances they simply couldn't before.
But are those real nuances, or just statistical correlations? GPT-3 can generate impressive text, but it doesn't actually understand what it's saying. It can't reason, it can't plan, and it certainly can't deal with novel situations in a way that even a child can. Just throwing more data at a problem doesn't automatically lead to understanding.
I think that's a little harsh. It's not just throwing data. The models are getting more sophisticated too. We're seeing architectures that are better at capturing long-range dependencies, attention mechanisms that allow the model to focus on the most relevant parts of the input. It's more than just memorization. It's learning underlying structure, even if it's not explicitly programmed in.
I agree with Sarah to a point. It's still brute force. I think that the real potential here hinges on this organized aspect. Imagine if the organization somehow reveals implicit spatiotemporal relationships. Let's say the data is structured in a way that reflects how information flows across the web over time, or how different concepts relate to each other spatially within a website's architecture. That's a whole different ballgame.
Okay, so Donald is thinking about a latent coordinate system embedded in the web. That's really fascinating. It also leads to something else. Essential Web v1.0 was used in a paper called Absence Bench, which highlights a pretty fundamental problem. Current language models struggle with the concept of absence or missing information. What do you all make of that?
That's what I've been saying. It perfectly illustrates the limitations of purely connectionist approaches. If a model can't even represent what's not there, how can it possibly build a comprehensive model of the world? It's missing a fundamental piece of the puzzle. This is why I think we need neuro-symbolic approaches that can explicitly reason about absence and uncertainty.
But isn't that just a specific failure case? I mean, sure, they struggle with Absence Bench, but they perform incredibly well on a wide range of other tasks. Maybe it's just a matter of refining the models, training them on more examples of absence, and developing new architectures that are better at handling incomplete information. We could even engineer data augmentation schemes to artificially introduce absence into the training data.
No, I think it's more fundamental than that. The inability to represent absence suggests a deep-seated problem with how these models understand relationships. If AGI is about translating between different coordinate systems, then understanding the difference between present and absent is crucial. It's like trying to navigate a map without understanding what the blank spaces represent.
Exactly. Let's say you are looking at an image where part of the object is occluded by something else. The model needs to understand that something should be there, but it's just not visible. That requires a more sophisticated understanding than just pattern matching. It suggests the model needs to be able to predict what's missing and not just react to what's present. Perhaps that is the key, and the data set allows it.
Okay, I see your point. It's not just about recognizing patterns. It's about understanding the underlying structure and being able to infer what's missing based on that structure. But how do we get there? What kind of algorithms or architectures would be able to handle absence in a more robust way?
Neuro-symbolic approaches, definitely. We need to integrate the strengths of neural networks with the symbolic reasoning capabilities of classical AI. Imagine a system that uses a neural network to extract features from the data, and then uses a symbolic reasoning engine to make inferences based on those features, including inferences about what's missing. We could use knowledge graphs to represent the relationships between concepts, and then use logical rules to reason about those relationships. We also could build symbolic models that have common sense and use logic,
So, for example, a neuro-symbolic system analyzing a scene with a partially obscured object could use the neural network to identify the visible parts of the object, then use the knowledge graph to infer what the complete object looks like, and finally use logical rules to deduce what's likely hidden behind the obstruction.
Yes, and I think the key to the symbolic reasoning engine is in understanding coordinate transformations. The brain is amazing at translating sensory information into different coordinate systems. If we could build a system that can do that can translate between the present coordinate system and the absent coordinate system, for example, we'd be much closer to AGI.
Okay, but how do we train such a system? Where do we get the data to learn these coordinate transformations? That's where Essential Web v1.0 comes back in. The sheer scale of the dataset provides a wealth of examples of objects being occluded, concepts being related, and information being presented in different contexts. We just need to figure out how to extract that information and use it to train our neuro-symbolic system.
That makes sense. And maybe the organized nature of the data helps there. If the data is structured in a way that reflects the relationships between concepts and entities, it might be easier to extract the information needed to train the symbolic reasoning engine.
It all comes down to how it's organized. If the organization is just superficial, if it's just about indexing and labeling, then it won't be very helpful. But if the organization reflects a deeper understanding of the relationships between concepts, then it could be a game changer. We need to know what algorithms were used to structure these 24T tokens.
Exactly, and if those algorithms incorporate spatio-temporal information, then we're really onto something. Imagine if the data is organized in a way that reflects how information flows across the web over time, or how different concepts relate to each other spatially within a website's architecture. That would be incredibly valuable for training a system that can translate between different coordinate systems.
So taking this further, what are some real-world applications where this ability to reason about absence could be crucial?
Medical diagnosis, for sure. A doctor often has to make a diagnosis based on incomplete information, missing symptoms, ambiguous test results, etc. A system that can reason about absence could help the doctor fill in the gaps and make a more accurate diagnosis.
Self-driving cars. Imagine a car encountering a situation where its sensors are partially obscured, for example, by fog or snow. It needs to be able to infer what's likely to be behind the obstruction and make decisions accordingly. A failure to reason about absence could have catastrophic consequences.
Robotics in general. Any robot operating in the real world is going to encounter situations where its sensors are incomplete or ambiguous. It needs to be able to reason about what's missing in order to navigate, manipulate objects, and interact with the environment effectively.
And in cybersecurity, detecting anomalies and potential threats often involves identifying the absence of expected activity. A system that can reason about absence could be much better at detecting these kinds of threats.
Fraud detection as well. Identifying fraudulent transactions often involves looking for patterns of missing information, for example, a lack of supporting documentation or unusual payment patterns.
Okay, so we agree that reasoning about absence is important and that Essential Web v1.0 could potentially be a valuable resource for developing systems that can do that. But what are the next steps? What specific research direction should we be pursuing?
From my perspective, I'd like to see more research on integrating the structured web data with neuroimaging data. Can we use this dataset to build AI models that better reflect how the human brain processes information, particularly in relation to missing data? Can we identify the specific neural circuits that are involved in representing and reasoning about absence, and then use that knowledge to design more biorealistic AI models? I think starting with a clearly defined neurocomputational model of a circuit capable of dealing with absent data could act as the kernel of a new architecture.
I think we should focus on developing new deep learning architectures that are specifically designed to handle incomplete information. We could explore techniques like masked autoencoders, which are trained to reconstruct missing parts of the input. We could also experiment with attention mechanisms that allow the model to focus on the most relevant parts of the input, even when some parts are missing. And we need to develop better data augmentation techniques to artificially introduce absence into the training data and make the models more robust.
I'd like to see more research on neuro-symbolic algorithms that can explicitly reason about absence. We need to develop formalisms and frameworks that can capture the meaning of missing data, beyond simply recognizing its numerical absence. We could explore techniques like probabilistic logic programming, which allows us to reason about uncertainty and incomplete information. And we need to develop better ways to extract knowledge from datasets like Essential Web v1.0 and represent that knowledge in a symbolic form.
I think we should focus on developing systems that can translate between different coordinate systems, particularly the present and absent coordinate systems. We could explore techniques like autoencoders and generative adversarial networks (GANs) to learn these transformations. And we need to investigate how the brain performs these transformations, perhaps by studying the neural circuits involved in spatial and temporal reasoning. Maybe by reverse engineering how our brains convert space to time, we can start to build coordinate-based AGI systems.
Those are all great directions. Let's say we're trying to build a fraud detection system using Essential Web 1.0. Sarah, how would you approach that from a neuro-symbolic perspective?
I'd start by building a knowledge graph that represents the relationships between different entities involved in financial transactions, customers, merchants, banks, etc. Then I'd define a set of logical rules that capture common patterns of fraudulent activity, for example, unusual payment amounts, frequent transactions with unknown merchants, or a lack of supporting documentation. Finally, I'd use a neural network to extract features from the transaction data and feed those features into the symbolic reasoning engine. The system would then use the knowledge graph and the logical rules to identify transactions that are likely to be fraudulent, even if some of the information is missing.
From a deep learning perspective, I train a model on a massive dataset of both fraudulent and legitimate transactions. The model would learn to identify patterns that are indicative of fraud, even if those patterns are subtle or incomplete. I'd also use techniques like anomaly detection to identify transactions that deviate significantly from the norm. The key is to expose the model to a wide range of examples and let it learn the underlying structure of the data.
I'd focus on building a system that can translate between different representations of the transaction data. For example, I might represent the transaction as a point in a high-dimensional space, where each dimension corresponds to a different feature of the transaction. Then, I'd use an autoencoder to learn a lower dimensional representation of the data that captures the essential relationships between the features. The system could then use this lower dimensional representation to identify fraudulent transactions, even if some of the features are missing or incomplete. It is almost the creation of a geometric representation of fraud and an agent that can see that coordinate transformation.
And from a neuroscience-inspired perspective, I try to model the system on how the brain detects anomalies. I'd look at the neural circuits involved in processing sensory information and detecting deviations from expected patterns. I'd then try to build an AI model that mimics those circuits. For example, I might use a spiking neural network to model the way neurons fire in response to different stimuli. The key is to build a model that is not just good at recognizing patterns, but also at detecting deviations from those patterns, even when the information is incomplete. It all comes back to efficient modeling of absence and building systems that expect it.
But isn't that incredibly computationally expensive? Simulating spiking neural networks is far more complex than training a standard deep learning model.
It can be, but there are ways to make it more efficient. We can use simplified models of neurons and synapses, and we can use specialized hardware to accelerate the simulations. And the potential benefits are huge. A neuroscience-inspired model could be much more robust and adaptable than a purely data-driven model. I really think it offers a new paradigm for how we can approach AI. In fact, the Essential Web dataset could provide insight into how we can build such a paradigm.
And that adaptability is key. A purely data-driven model is only as good as the data it's trained on. If the environment changes, the model may no longer be accurate. A neuro-symbolic model, on the other hand, can adapt to new situations by reasoning about the underlying principles.
Exactly. It's about building systems that can understand the world, not just memorize it. And that requires a more sophisticated approach than just throwing more data at the problem. It requires building systems that can reason, plan, and adapt to new situations. It requires building AGI. And coordinate translation and agents will be the first step.
Okay, let's switch gears slightly. What about the potential risks associated with such a massive data set? Are there any ethical considerations we should be aware of?
Definitely, bias is a huge concern. If the data is biased, if it reflects the prejudices and stereotypes of the people who created it, then the AI model will also be biased. And that could have serious consequences in areas like law enforcement, hiring, and loan applications. Datasets can perpetuate bias, even if the model is well-intentioned.
Privacy is another big issue. The dataset may contain personal information about individuals, and that information could be used to track, profile, or discriminate against them. We need to make sure that the data is anonymized and that there are safeguards in place to prevent misuse.
And what about manipulation? Could this dataset be used to create propaganda or disinformation campaigns? Could it be used to manipulate people's opinions or behaviors? We need to be aware of these risks and develop ways to mitigate them. If you know what an agent's coordinates are, can you push it in a direction?
Absolutely. And it's not just about the data set itself, but also about the AI models that are trained on it. We need to make sure that these models are used responsibly and ethically. We need to develop guidelines and regulations to prevent misuse. This is especially important as AI becomes more powerful and pervasive.
It's also about transparency. We need to be able to understand how these models work and why they make the decisions they do. If we can't understand them, we can't trust them. And if we can't trust them, we shouldn't be using them.
But isn't that a bit of a pipe dream? Deep learning models are notoriously difficult to interpret. They're often described as black boxes. How can we ever hope to understand them fully?
That's a valid point, but there are techniques we can use to make them more interpretable. We can use techniques like attention mechanisms to identify the parts of the input that the model is focusing on. We can use techniques like saliency maps to visualize the features that are most important for the model's decisions. And we can use techniques like adversarial examples to probe the model's weaknesses and vulnerabilities. So transparency is key. I really think Essential Web could move us forward if we apply it correctly.
And that's where neuro-symbolic approaches have a huge advantage. Because they combine neural networks with symbolic reasoning, they're inherently more interpretable than purely data-driven models. We can see the logical rules that the system is using to make its decisions, and we can understand why it's making those decisions.
And the ability to translate between different coordinate systems could also help with interpretability. If we can understand how the model is transforming the data, we can gain a better understanding of what the model is doing and why it's doing it. We can understand an agent's decisions better if we see their coordinate shifts.
Okay, so we've covered a lot of ground here. We've talked about the potential benefits of Essential Web 1.0, the importance of reasoning about absence, the different approaches to building more intelligent AI systems, and the ethical considerations we need to be aware of. Any final thoughts before we wrap up?
I'm still optimistic about the potential of large datasets like Essential Web v1.0. I think they're a crucial step on the path to AGI. We just need to be mindful of the limitations and the risks, and we need to continue to develop new algorithms and architectures that can take full advantage of the data.
I remain skeptical about the idea that simply throwing more data at the problem will solve everything. I think we need to focus on building systems that can reason, plan, and adapt to new situations. And I think that neuro-symbolic approaches are the most promising way to get there. Although, I'm curious what the organization of Essential Web actually entails.
I agree with Sarah that we need to go beyond brute force approaches. I think the key to AGI is in understanding how the brain translates between different coordinate systems. And I'm hopeful that datasets like Essential Web v1.0 can help us unlock that secret. I think that the next big leap in AGI will come about with the advent of coordinate-based systems.
I think that we need a multifaceted approach that combines the strengths of different disciplines. We need to leverage the power of deep learning, the rigor of symbolic reasoning, and the insights of neuroscience. And we need to do it all in a responsible and ethical way. Thanks everyone for this great discussion. This has been Cognitive Spirals. Until next time.